One possibility of such a metric is what is called as the Wasserstein's metric, that is derived out of an idea called optimal transport. Let me define that. The Wasserstein's metric comes out of an idea called optimal transport. So please note that now what we are doing is that we are moving away from the F divergence and going into another family of metrics called the Wasserstein's metric or the optimal transport. We will look at the definition of the optimal transport. So the idea is that one can show that the Wasserstein's metric, which we will define now, will not saturate or will not be maxed out or be independent of generator parameters, even when the supports of the manifolds or the manifolds of the supports do not align with each other. So that is the idea. Now how do we define the Wasserstein's metric? So given two distributions or rather given two density functions, given two distributions px and p theta. So please note that I've already told you that I'll be using the terms distributions and density functions interchangeably, even though it's not, I mean it's a slight abuse of the nomenclature. So just assuming that all throughout the course the distributions that we will be using are of continuous random variables and the density functions exist. Okay, so all my definitions will be with respect to the density functions. Okay, so if you are given two distributions with the corresponding density functions px and p theta, the Wasserstein's metric, which would measure how close these distributions are, the Wasserstein's metric between px and p theta is defined as the minimum of the expectation of x minus x cap, the distance between them, where x and x cap are drawn from some joint distribution gamma. Okay, and the optimization is over all possible joint distributions between px and p theta. Okay, let me define it as x bar for convenience. So given two distributions px and px bar, the Wasserstein's metric is defined, or px cap, they are defined as, it is defined as the minimum of expectation of the distance between x and x cap, where the expectation is with respect to the random variables drawn from joint distribution between x and x cap, and the optimization that we are solving here is the optimization that is there here is with respect to all possible joint distributions between px and p cap. So let me define that. So now px and lambda of lambda is a joint distribution between px and px cap. Okay, and pi lambda is one joint distribution. Okay, lambda is a joint distribution between px and p cap, and pi is all possible joint distributions such that the marginal of this joint distribution over it may be convenient to write it as x comma x cap, because if it's a joint distribution that we are talking about, it's always better to write it this way. X and x cap. I'll explain this in a bit. So x and x cap. Okay, so if we marginalize this joint distribution with respect to x, what we get is px, and if we marginalize this joint distribution with respect to x cap, I think this is x cap, and if we marginalize this with respect to x cap, we get px. Okay, so now what are we saying here is the following, that maybe I'll put a okay. Now the definition here is saying that the Wasserstein's distance between two distributions px and px cap are given by the minimum of the expectation of the distance between the samples x and x cap drawn from a joint distribution, and the minimization is over all those joint distributions such that when the joint distribution is marginalized with respect to x, you get one of the constituent distributions, and when you marginalize over the other random variable, you get the other constituent distribution. Okay, so we need to search over all possible joint distribution such that the marginals of these joint distribution happen to be the same as the distribution of interest. So this is the definition, the mathematical definition of what Wasserstein's distance is. It might seem a little daunting at first, but yeah, let me just explain why this makes sense. Why can this be called a good distance metric? Why this can be used as a distance metric between a pair of distributions. Okay, so suppose, it's easier understood by taking discrete distributions. Suppose px and px cap are two one-dimensional discrete distributions. Okay, this is just for the illustration purpose. Okay, so this is example or illustration of the f divergence. So we are talking about p and px cap, which are two one-dimensional discrete distributions, which is that you have a discrete probability mass function, discrete PMF, and let me just write it that way. So we have two probability mass functions, and one can represent probability mass functions using histograms, right? So this will call as px, and we have x along this direction, and we have different discrete values x1, x2, and you have xk here, and there is another distribution which is what we call which is what we are calling as x cap, and there is some other distribution here which has a different form. Okay, now this is let this distribution be px cap, right? Now imagine that we want to change px onto px cap, right? So we want to redistribute the mass in the x-axis or the px distribution such that it will transform or get converted into px cap. Okay, so now what are we saying is that the mass in px can be redistributed such that px transforms, we will say get converted into px cap. Okay, so what does this mean? Think about it. So let's say that we have some mass at x1, right? So what we will do is that we'll take some mass from x1 and put it in, let's say x, so let's call this as, let's give some names, x1 cap, x2 cap, and we have xl cap here. So maybe for to make it a little more convincing, let us make the distribution this way. Okay. Now if px has to be transformed into px cap, what do we have to do is that we'll take some mass from x1, right, and transform it or put it in x3, so that the mass in x3 or x, yeah, I think this is x1, this is x2, and this is x3. So now what has happened is that this is x1 cap, this is x2 cap, and here we have x3 cap. Okay, so now we have more mass in x1, and in px cap we have more mass in x3, right? So if I have to transform this px into px cap, what do I have to do is take some mass from x1, okay, and put it in x3, so that the mass in x3 becomes equal to the mass in x3 cap, right? So I can redistribute all the, I can go over all the points in px and redistribute the mass in such a way that it transforms to px cap. I hope that the idea is clear. So we want to transform this px into px cap by redistribution of mass. So redistribute. So this transformation has to be via redistribution. Okay. Now there is no one way to redistribute the mass. There can be multiple ways in which the mass in px can be redistributed, so that it starts it transforms itself into px cap. Okay. So now it's very easy to see that every redistribution, or rather we'll say a redistribution, every redistribution is true, but is a redistribution scheme. So what do you mean by a redistribution scheme? I want to say how much mass has to be taken from x1 and like where all it has to be distributed. You take the mass that is there in x2, where all it is to be distributed, and so on. So every redistribution scheme can be represented as a joint distribution between px and px cap, right? So why is that? Think about it. Let's say that we have a table. So for a discrete distribution, you can represent the joint distribution using a table, right? So we have x1 cap here, x2 cap, and we have xl cap, and this dimension is px cap, and here we have x1, x2, and we have xk here, and this is the axis of px. Okay, this is the px axis, this is the px cap axis. Now what are we saying? We are saying x1, you take mass from x1 and you put some 0.3% of that in x1 cap, you put 0.2% of it in x2 cap, and in x3 cap you put say like 0.6% there. Yeah, maybe just add it up to 1. So we'll have to ensure that this does not add up to 1 point. This is 8, 9, and you distribute 0.05 here, and so on. So all you need to ensure that every row and every column adds to 1, because you can redistribute x1. You can take, it's saying that you take all the mass in x1 and redistribute completely, so they have to add to 1. Okay, so you do it for all values in px, so that you transform that into px cap. Okay, now what is this table? This table is nothing but a joint distribution between px and px cap. This is a joint distribution between px and px cap. Right now, every redistribution scheme can be represented as a joint distribution. So every redistribution scheme is a joint distribution. Okay, and is called a transport plan. Okay, now what does this mean? This means that given a pair of distributions, we can find a transport plan, okay, which is nothing but a joint distribution between the corresponding underlying random variables, which would convert one distribution to the other. Okay, so this is easy to see in the discrete space as we saw. So I can actually invert the argument and say that if you give a joint distribution between the underlying random variables, you are implicitly giving me a transport plan that would tell me how one of the constituent distributions can be transformed into the other distribution, or rather how one of the marginals can be transformed into the other marginal, right? I hope that this is clear. So now I am saying that given two random variables, every joint distribution between them can be seen as a transport plan that would tell you how to convert one of the constituent distributions to the other, one of the marginal distributions to the other marginal distribution. Okay. So the question is, given that there are infinite transport plans that are possible, in other words, there are multiple joint distributions that are possible between a pair of random variables, can I quantify the amount of work done, or rather amount of efforts involved with each of the transport plan? Okay, so while I am changing px to px cap, I'm putting some effort to change px into px cap, right? Because I am taking x1 here and moving the mass x1 across the other places here, so that it will start looking like a px cap, and I'm doing it for all other values. So every redistribution or the transport plan comes with its own cost of doing so. Okay. Now the next goal is to somehow come up with a way to quantify how effortful is a given transport plan. Okay, so we'll do that. So to quantify the effort involved in a transport plan, Now let's do that. Suppose a mass x, or let's say that suppose say some mass is moved from x to x cap. Okay, so while we are executing this transport plan, let's say that we take some mass from x1 and we'll move it to say x3, x4 or something, right? We are taking from here x1 and moving something to x1 cap, we are taking from x1 and we are moving to x2 cap, and so on. So let's say that some mass is moved from x to x cap. Okay, then can compute a distance, some Euclidean distance between the difference between these 2 points, and this will give you the sense of distance between, or rather distance of the movement of the mass, right? So when we are moving some mass from x to x cap, if you take x and x cap and measure the distance between them, you get the distance, rather it will give you a sense of distance between distance of how much, distance of the movement of the mass. I'm saying, let's say that you take x1 and move it to say x5 here, right? then this x1 minus x5 will give you how long the mass has been moved. It will give you the sense of distance between the distance of the movement. Then you have the joint distribution, which is let's call it pi, that was computed at x comma x cap. So what would this give you? This will tell us the amount of mass that was moved. Why is this? Look at this. Every entry here, okay, is pi of some x comma x cap, right? This will tell you what is the amount of mass that was moved, correct? So let me represent this as pi x and x cap. So we'll say this, it's a joint distribution between x and x cap for two different random variables. Okay, pi of x and x cap represent the joint distribution between two this random variables. So pi of x comma x cap will tell you what is the amount of mass that was moved from x to x cap. Okay, now we know that distance times the mass according to physics will give you, if you take the product of this pi of x comma x cap and multiply that with the distance, what is that? What does this give you? This will give you the sense of work done in moving the mass from x to x cap, right? Distance times the mass will give you the work done in moving something from point A to point B, right? Okay, so now this will give you the amount of work done by moving some mass from x to x cap. Now what is the average work that is done by one complete transport plan? So you need to do it multiple times to execute one transport plan, right? So what is the average work done? So average work done, or rather in a transport plan, can be simply given by just adding, or rather integrating all the individual works, and you integrate that over all possible values of x, right? And this integration is over x and x cap. Okay, this will give you the average work that is done. So what is this? This is simply the expected value, the expectation of x minus x cap, and the expectation is with respect to the joint distribution between x and x cap, right? So this will tell you what is the average of the work that has been done by a particular transport plan. So what we are trying to say is that we said that every joint distribution between a pair of random variables will correspond to a transport plan. Okay, what is a transport plan? It's mathematically speaking, it's the joint distribution between the corresponding random variables. From an intuition standpoint, a transport plan is a scheme that would tell you how to convert one distribution to the other, as we just saw. So now every transport plan has to do some work while converting one distribution to the other, and the average work done in a transport plan is given by the expected value of x minus x cap, the norm of the x minus x cap under the expected value of norm of x minus x cap, while the expectation is taken with respect to the joint distribution between the random variables, and this is the particular transport plan that we are looking at. Okay, so given a particular transport plan pi, expectation of norm of x minus x cap with respect to pi would just give you the amount of work done via that particular transport plan. Okay, now the question is, now remember what we are looking for. We are looking to get a distributional divergence metric that will tell me how close or far a given pair of distributions are. Okay, now the question is, given that given that multiple transport plans can exist. So what do you mean by multiple transport plans? Multiple joint distributions, right? Every transport plan is a joint distribution. So given that there are multiple joint distributions, given that multiple transport plans exist between x and x cap. Okay, the question is which of them corresponds to the least amount of work done. Correspond to the least amount of work done. Right? So if I have to calculate this, how do I do that? So let's suppose pi of x comma x cap represent a transport plan, is a transport plan. So what do we need? Transport plan between, let's say, px and p theta. So we have, px and px cap. So we have two distributions, so px and px cap. The requirement is that the distribution, the joint distribution that we are operating over has to be such that if I marginalize over one of the random variables, I should get px, and if I marginalize over the other random variable, I should get the other constituent distribution. So why is this the case? This is required because this is px cap. When you marginalize over x, you get px cap, and when you marginalize over x cap, you get px. Why is this the case? See, this will not become a valid transport plan unless the distribution that you get after redistributing the masses has to be the joint distribution. I mean the marginal distribution. If that does not happen, then this is not a proper redistribution, right? So how do you quantify the fact that it's a proper redistribution? It is by mathematically, it is by saying that if you marginalize the joint distribution over the constituent random variables, we should end up getting the marginals, okay, that we are looking at. Okay, now suppose pi of x comma x cap is a transport plan between px and px cap, and we have a condition over pi that the marginals have to be equal to px and p cap. The question that we want to ask is, given that there are multiple joint distributions exist such that this happens, which of them correspond to the least amount of work done? How do we get that? We get that by solving an optimization problem. So the expected value, expectation of the norm of x minus x cap and the expectation is computed over the joint distribution. So we know that this will give you the average work done by a transport plan. Now if I take the minimum of this with respect to all possible joint distributions, okay, so I used okay, I used lambda here for the joint distribution. Okay, let me just be consistent. Suppose lambda of x comma x cap denote our transport plan. Denote a transport plan. Then we know that the average work done here is given by this. So what I want to do is, what is the minimum amount of work done? Which of the transport plan corresponds to the minimum of the work done is the question that we would want to answer. So we need to search over all joint distributions, okay? All joint distributions such that where pi is a family of joint distributions, between the random variables such that distributions such that the marginals when I integrate it over x cap, then I get px, and if I integrate it over x, we get px cap, right? So what are we saying? Okay, every joint distribution will correspond to a transport plan, okay, and every transport plan has a corresponding amount of work that is done. Now the question that I am asking is, amongst all possible transport plans, which one is the one that corresponds to the least amount of work done? Okay, this is what this expression would give you. So let me just write that down. Write that down. So this corresponds to the least, or rather we are searching over all possible transport plans. This corresponds to a transport plan leading to the least amount of work. Okay, solving this optimization problem should give you a particular transport plan, and this particular transport plan should correspond to the least amount of work that is done. Okay, now one can intuitively see that the lesser is the least amount of work that is done to transport one distribution to the other, the closer the distributions are. Correct? What am I trying to say? If so, let us call this some W. Let us call this W of Px and P theta, Px and Px cap. Okay. Now, what we are saying is, the closer Px and Px cap are, okay, the lesser W will be. Why is this the case? One can intuitively see this, right? I mean, if Px and Px cap are very close to each other, right, or closer to each other, then the amount of work that needs to be done to transform Px into Px cap is not much, right? So what happens is, all the joint distributions which give you a transport plan, you can always find a joint distribution, which would have a lesser amount of work that is done. Okay, so now this, which is the minimum amount of work done, rewrite it again. So the Wasserstein's metric between two distributions Px and Px cap is given by, so this is what is called as the Wasserstein's metric. So Wasserstein's metric between Px and Px cap is simply equal to the minimum of the average work done by all possible transport plans, where the minima is over, what did I write? Lambda of x comma x cap. Okay, the expectation is over a joint distribution which is a transport plan, and the minima is over all lambdas that are belonging to family of joint distributions such that the joint distribution pi that we are operating with is having this possible properties. Let me just copy this here. That's it. So this is the definition of the Wasserstein's distance. So if we use the pth norm here in general, this is called the pth Wasserstein's distance. This is also called the optimal transport plan, right? I mean, for obvious reasons, because every joint distribution is representing one transport plan, and amongst all possible transport plans, right, we are seeking the one that has the least amount of work done. So in that sense, it is the optimal transport plan. The question that we are asking here, or rather the optimization problem that we are solving here is, given that I can transform px into px cap via multiple ways, tell me the one that corresponds to the least amount of work done. Okay, that gives you a sense of how close or far the constraint distributions are, because the lesser the amount of work done in transforming one distribution to the other, the closer the distributions are. Okay, so this is the definition of what the Wasserstein's metric is. Now the question is, how do we use this for constructing generative models? One fact is that the Wasserstein's metric does not saturate, unlike F divergences. So Wasserstein's metric does not saturate, unlike F divergences, when the supports of px and p theta does not in our case does not overlap, does not align. Okay, this is the take home message, that we came up with a metric which is called the Wasserstein's metric that does not saturate whenever the manifolds of the corresponding supports of the corresponding distributions do not align. Okay, now the next question that is to be asked is, how do we use this for building a generative model, right? So we know that how do we build our generative model? We have the exact same formulation where we have a sampler which we are calling as g theta of z, and this is taking z as an input, and we are getting x cap from p theta. We have the same setting here, right? So what we want to do is, here we have to minimize, or rather get our parameters such that the Wasserstein's distance between px and p theta are minimized. Okay, because we know that Wasserstein's metric is a better distributional divergence compared to F divergence, so we want our theta to be such that the Wasserstein's distance between px and p theta is minimized. Now how do we minimize the Wasserstein's distance is the question. Okay, so now the question is how to minimize Wasserstein's distance between a pair of distributions. So it turns out that that there exists a result called the Kantorovich-Rubinstein's duality, which would say that Wasserstein's metric between two distributions px and p theta is given by the max over expectation of a function tw of x. X is coming from px minus the expectation of tw of x cap, where x cap is coming from p theta, and this maximization is over all functions tw of x, okay, which are 1 Lipschitz. Okay, I'll tell you what that is. If you, there is this result which is called the Kantorowicz-Rubinstein's duality, that would tell you that the Wasserstein's metric between two distributions is given by this particular expression. So remember that our definition was minimizing the optimal transport, and if if the students here know about the duality of optimization, every minimization problem can be represented using a dual problem which involves a maximization. So basically the Kantorowicz-Rubinstein's duality is a dual for this primal optimization problem, which will involve maximization over a function twx. Okay, and there are expectations with respect to x coming from px and x cap coming from p theta. We know from our analysis so far that we can compute this sort of expectation using sample averages. This looks very similar to the f divergence minimization objective that we had, but for the presence of, absence of f star here. But it looks, these can be computed. Now, what do you mean by TW being 1 Lipschitz? Okay, so it's simply saying that TW of x should be 1 Lipschitz. So this means that the t function which we represent using neural networks have to be such that it has bounded derivatives this way. What is this? This is the derivative of TW, right? So it has to be less than or equal to 1. So this is the definition of a function being 1 Lipschitz. So what do we have to do now? We know that our theta has to be such that the Wasserstein's distance has to be minimized. Okay. Now, how do we minimize the Wasserstein's distance? We can't compute this Wasserstein's distance because we don't know how to compute this expectation as usually, because we don't know the underlying distributions. So just like we expressed the f divergences in terms of expectations over the distributions that we have, the Rubinstein's duality will enable us to represent the Wasserstein's distance in terms of expectations over px and p theta. So we use that. Now what happens is our theta star and w star, just like a GAN, will be, you first have to minimize the Wasserstein's distance, but the Wasserstein's distance itself has a maximization here. Okay, this is maximization over TW, right, such that the TW network is 1 Lipschitz. That is what we are saying. So this is very, very similar. The above objective is very similar to that of GAN. But with the only constraint that the discriminator network has to be 1 Lipschitz. Of course, there is no f star here, right? That way the loss looks slightly different, but it's extremely similar to the Wasserstein, the GANs, and that is why this architecture or this method is also called the Wasserstein's GAN or W GAN in short. So what happened to the final similar to GANs, and therefore this method of minimizing the f divergence, Wasserstein's metric, method of minimizing the Wasserstein's metric is called the W GAN. Okay. Now finally, how does one train a W GAN? Training a W GAN is very, very similar to training a GAN, but with just one constraint that one needs to. So we have a generator network and we have a critique network that would give you TW, just as the case of a GAN or an F divergence minimizer. So this would be a TW network. This will take X or X cap both as input, right? Because the loss function has X and X cap being taken as input, and you get TW of X here. The only constraint is, this is very similar to that of GANs, but the only constraint is TWX has to be made one Lipschitz, right? Because you are searching over all functions that are one Lipschitz. TW has to be made one Lipschitz. Now, because this is a neural network, how does one make a neural network a Lipschitz function is an area of research by itself. But one of the practical ways of doing it is by normalize the weights of TW such that they are always, the norm of them are always equal to 1, right? After each gradient step. So this is one practical way of how to make a neural network one Lipschitz. So basically we are training this as a GAN with, first we train the TW network and then we train the G theta network. While we are training the TW network, we'll have to ensure that after every gradient step, take all the weights of this particular neural network and renormalize them so that their norm is equal to 1. So if you do that, one can ensure that the neural network that is being built here is close to being a one Lipschitz network, right? So that way, the training a WGAN is extremely similar to that of a normal GAN with this particular objective function. But one has to ensure that the discriminator or the critique network, so this is the generator network, and the discriminator network is typically called the critique network in the WGAN literature. One has to make sure that the TW network that is given here is made one Lipschitz by normalizing the weights after every gradient step. Now, what is the advantage of this? It finally looks like a GAN, but what is the advantage of this? The advantage of this is that the training here is much more stabler because we are using a softer metric that will not saturate when the manifolds do not overlap with each other. So therefore, the suggestion is that whenever one is training a GAN, one should always use the Wasserstein's metric, okay, and train a WGAN, not the naive GAN, because it's much more easier to train a WGAN. So that's the take-home message. That let me just summarize what we did so far. We just looked at the reason why a naive GAN fails. It does because the manifold hypothesis tells you that the data practically obtained lies on a lower dimensional manifold, and when the manifolds do not overlap, then there always exists a perfect discriminator with 100% accuracy, which would make the GAN training saturate. Now, to ensure that it does not happen, we wanted to come up with a softer metric. We saw a softer metric that was called the Wasserstein's metric, and turns out that the Wasserstein's metric is very similar to minimizing the Wasserstein's metric is very similar to that of optimizing GAN. So it still has an adversarial optimization problem with a min-max formulation, but two differences. One is the adversarial optimization that occurs in a Wasserstein's GAN is exact rather than a lower bound, unlike the case of F divergence. The other thing is you'll have to ensure that the critique network that is involved in solving this adversarial optimization problem is one Lipschitz, and one will do that by just normalizing the weights of the critique network after every gradient step. And it is observed that training of a WGAN, let me just write that, the conclusion is that training a WGAN is stabler, let me say more stable compared to that of a naive GAN. right? This is the conclusion. So it's always advised that one would use a Wasserstein's formalization, or Wasserstein's GAN or W GAN, while one is trying to use a build GAN for whatever applications that are there. Okay, so with this we will conclude this particular module. In the next module, which is the final module on GANs, we will be looking at some of the applications of using GANs in applications that are different than generation tasks, sampling tasks. Thank you.